Okay, so the formula is for the refractive index under special circumstances, that is. So refractive index was, we had done two formulas. The first one was sine of I divided by sine of R, and its essence was sine of rare divided by sine of dense. Do you remember that? Yes. And the other formula was n equals to c divided by v, where c was a constant, that was speed in vacuum, and v was the speed in any other medium that it's trying to travel through. Another formula for refractive index for critical angle is as follows. The formula comes out as n equals to 1 over sine c. And let's look at this, although it's not a part of your course, how to find out how the formula and why this formula is actually formulated, but I'm going to discuss this because it makes it easier to remember. You see, the condition for total internal reflection arrives when the light ray actually travels from a dense medium to a rare medium, and it's bending away from the normal like this. And the extreme condition was that when it actually bends at 90 degrees or starts moving parallel to the surface. In that case, this angle of incidence was referred as angle or critical angle and was labeled as C. It is the incident angle in the dense medium, but now it will be called as critical angle. So if I put this formula or these values in the refractive index again, just a moment. Can you hear me? Okay. Okay, just a moment. So whatever these values may be, we have sine I divided by sine R. And if you notice that the upper angle used to be for the rare medium and the denominator angle used to be for the dense medium, right? So let's replace or let's figure out where those angles are. So rare angle is over here, that is 90 degrees. And dense angle is over here, which is now labeled as C. So the formula becomes n equals to sine of 90 divided by sine of C. When we calculate, yeah, so when we calculate sine, yeah, so when we calculate sine 90, that becomes 1, and then that becomes 1 over sine of C, not 1 over C. Okay. So for critical angle, if the refractive index is given to you, because this formula is equal to the refractive index, either the examiner gives you the refractive index or the critical angle, whatever they try to give you, you can find out the respective quantity. Okay. And over here we can analyze one more point, and that would be that the refractive index is actually inversely proportional to the critical angle. What would that mean? It means that, for example, if we have a medium that has a refractive index of 1.5 and this one has a refractive index of 2.0, be that refractive index. So visually speaking, even if we are expecting both light rays to exit at 90 for this activity, then the one that has less refractive index, that is 1.5, its critical angle will be larger as lesser the refractive index, higher will be the critical angle, and vice versa for the other case. So let's say this is, for the sake of example, let's say if this is 40 degrees, this might come out as 25 degrees. So if you increase the refractive index, the critical angle's value falls. This is just a comparison for an MCQ trick. Otherwise, there's nothing more to it. Okay. All right. All right. So that is all for the chapter of light. The next topic that we have to start is lenses, a thin lens or converging by a thin lens. So there are two types of lenses in your syllabus, and by this time we are familiar with two terms. And the first one is converging, We know what that means. It means that light rays are trying to focus at a single point. And the other term that we are familiar with is diverging. So, light rays are actually moving out from a point source outwards. So, a diverging example would be our tube light, our simple energy saver light, or the light coming from the sun. That light is actually diverging outwards because sun is considered as a point source and it is spreading out its light throughout the universe or throughout the galaxy, right? Okay, so we are familiar with these two words, and we have two types of lenses with respective qualities. The first one is convex lens, and the second one is concave lens. So a convex lens would look like this in real life, and a concave lens would look like this in real life. These are highly exaggerated images, of course, just to make sure that the students understand. Otherwise, to naked eye, they don't appear as curved as this one. Okay, so light rays traveling towards this lens, they will converge at a single point like this. And light traveling towards this concave lens, which actually spread outwards like this. Yes, do we understand this point? Okay, so it's your job to remember that a convex lens is a converging lens and a concave lens is a diverging lens. Okay. Now, in our case, in our syllabus, what we have to do is we have to learn how to draw the ray diagrams. How do we draw them? Now, let's look at what are ray diagrams and what we are actually looking at. So, do you remember that we were looking at a diagram for the plane mirror at the very beginning of this lesson when we started this chapter? So based on that, now we're going to draw ray diagrams via lenses of the objects that, for example, are trying to be viewed through them. So first, you need to remember that there must be two rays emitted or being considered from every object. Okay, and a second would be that we must draw them with a ruler. We are assuming that they're traveling in straight lines. Do not draw them freehand. Okay. The most important point will be this one because the second point is intuition based. Students generally do understand that they're supposed to be straight, but they forget about the first one that there are always going to be two light rays coming from every object, right? And what do we mean by that statement? Let's try to look at it. Okay, so let's draw a ray diagram for a mirror. And there are two cases. The first one is a point object. A point object will be considered as an object that is purely one-dimensional. It has no length, no width, no height. So it's easy to visualize it that way. The other one will be considered as an extended object. Now, extended objects are two-dimensionals. They are not three-dimensional. Again, a three-dimensional diagram on the notebook would be a quite hectic process, so that's not a part of the course. But two-dimensional extended object is. We will get to that later. So let's try to draw the first one. How to look at this diagram. So this will be your mirror, for example. This is your real side where the actual object is being placed. For example, you're standing out of the mirror, so you're in the real world. Whatever is being formed inside the mirror is going to be considered as virtual. I believe that we understand what is the difference between the two terms as well. Do you remember that? Right. Okay. Sorry. So, for example, this is the object. I will label this as O, which we are trying to view through the mirror. So I will not directly view this object with my eyes. Rather, I will place my eyes in such a position that help me view the object through the mirror. So I'm actually looking into the mirror, expecting to see this object. Do you understand the setting? Right? So you observe this or you do this every day when you're trying to look at yourself in the mirror every morning, right? So when you're looking at your face, you're looking at your hair, whatever you're looking at, this is what the ray diagrams are actually, this is how they're being formed. So these are your eyes or the position of the eyes. Okay. All right. So the first thing is that the distance after measuring with the ruler, the distance outside the image should be exactly the same inside the image, right? So you take a ruler, you make these measurements, and you draw precisely the location where this image is supposed to be. So I will label this as capital I. So the first point is that the distance of object is equal to distance of image. Okay? And if you remember that when we were talking about mirror, I discussed that point over there that however whatever distance you have outside the mirror, the same distance you will see your image inside the mirror as well. Do you remember that? Plane mirror qualities? Yes? Okay. So let's move to the next part. Now, let's go back to the first point that we did, that there's supposed to be two rays from every object. Why there need to be two rays? We will get to that later as well. There is a reason for that. You see, I am viewing this object. I am not looking at this one that is on the outside because I'm looking at the image of that object that is inside the mirror, right? So what I'm going to do, I'm going to use my ruler in this way. I'm just trying to tell you how to draw the diagram most conveniently. So I'm going to place my ruler like this. Okay. I'm going to draw dotted lines for the virtual side, and then I will deliberately draw solid lines for the real world. Do we understand this part? Okay. Then I'm going to I'm highlighting this over there. So dotted for virtual side, and solid line for a real side. This is how on examination, or this is how on paper, you as a student and him as an examiner differentiate that are you talking about real side or are you talking about virtual side. So he will not tell you which one is real and virtual, but he will give you this indication. At some places it will be a solid line, at some places it will be dotted line. So by looking at the type of line, you can guess whether this is virtual or real. So this is an important part. Please keep that in mind. Okay. All right. So okay. So what we have done, why two rays? Because we have to cover the whole eye. So one light ray is supposed to be received on the top end of the eye, and one is supposed to be received at the lower end of the eye. Basically, if we go a little deeper into this, there are infinite light rays coming towards the eye, being originated from the object, from this point object, but it's not feasible to draw all of them. So what we do as a compromise is that we assume that, for example, if we can successfully cover the whole eye, the top part of the eye and the lower part of the eye, we would assume that naturally other light rays must also have covered the eye and successfully enable this eye to view the object that it is trying to view in the first place. Do we understand the idea? Why there are two rays? Okay, so the second ray that I'm supposed to draw, again, I'm going to place my ruler the same way I placed it before. Uh, So over here, dotted line, I'm just drawing it freely with rough hand, so I'm not able to draw them straight, but you will draw them straight with the help of the ruler. Okay, the other line will come at the top end, right? So now the whole eye is covered. Actually, this line is also a bit far away. I would like to make it better. So this is actually supposed to be at the lower end of the eye, and we have to be very precise about that. Okay? All right. So now we have to understand where did they actually come from. Is this image actually in the virtual plane? No. The actual object that caused this image is actually on the real side. So what's happening is that these light rays are actually originating from the real world, bouncing off the mirror, and then being received into the eyes. Do we understand this point? So that is how the light ray is actually bouncing off from your hair, from your face, from whatever you're trying to look at around you, from the mirror, of course. Now, some students, what they generally do is try to draw this diagram in this way, that first they try to draw a line, and over here we have the eyes, and then they try to match it here. Then they draw the line, and then they match it here. The problem with this diagram is in the details. So when you're trying to take this measurement and trying to draw the dot over here, it is almost with 90% certainty that students are unable to join the lines back over here. Why? Because they look awkward. How do they look awkward? Let me tell you. So when they try to extend this line, even with the ruler, a dot appears here, but this line actually intersects before it. So there are two dots that are actually appearing on the line, and the lines are not even straight. So it looks very bad. So the way around this, or to cater this, what we have done, what I've told you, is that first draw these lines. First, get rid of them, because after that we only have to draw them at the points of intersection on the mirror, right? So it actually eliminates any sources of error or any minute miscalculations of the angle. Do we understand how to do it properly? Okay. Mm-hmm. Yeah, yeah, yeah. Yep, yep, yep. So this one will be my step one, and this one will be my step two. Okay. All right. So this was a point object that would mean it's one dimensional. It doesn't have length, breadth, or width. This is how we draw that, and then we go back to the extended object. Okay. So for that, again, we have a mirror. Let me show, I think, another screen for that. Then I'm going to draw it roughly. Let me show the whiteboard because that would be better at that place. Okay, so just a moment. Can you see this on the screen? Okay, so this is our mirror, right? And this is our extended object. An extended object would have length and breadth, but not width. It will not have any, you can say, a third dimension, right? So these are our eyes right now. Sorry. Okay. All right. So my first job would be as a student is to measure this distance and measure this distance. Then I'm going to replace the same distances on the other side, like so, and draw my extended object on the other side, like this. Do we understand what we've done? Okay. So again, after drawing this, what I'm going to do is I'm going to draw one straight line from the lower part to the eyes and one straight line from the upper part, apologies, to the upper side. Sorry, not this way, but okay. So from the lower part to the upper side. Do you see what we have done? What we're trying to do, of course, I'm going to draw the dotted line afterwards, but do we see what we've done? What I have tried to do is I've tried to ensure that the lower part of the arrow is visible to the whole eye. So one light ray has to actually be received at the top end and one light ray at the bottom end. So that is what we mean by two light arrows per object or per side, right? Okay. So after this, we have to view or successfully view the top part of the eye of this arrow, and then also manage this to be visible to the lower part of the eye. Do we understand what we've done? Any issues? Okay, okay, okay. Now what we're going to do is just simply connect with the ruler again all the points of intersection that we're observing here with the mirror with the actual origin of the object where the object is actually originated from. So, but be advised that the lower part is actually the pink line and the upper part is the red line. So the lower part is supposed to be connected with the pink ones. Do not connect them with the red ones. Okay. And the top part is supposed to be connected with the red one. And then again, the top part is supposed to be connected with the red one that is a bit over here. Okay. Is it acceptable? Do you understand? Now, the only thing missing here is that when you're going to draw this in real life, make sure that you draw these lines as dotted lines. They're supposed to be dotted. Okay, that's the only thing that was missing. Yeah. Hmm. Yes. So the lower part of the object is also visible to the eye, the upper part and lower part, and the upper part of the object is also visible to the eye, covering it from top to bottom. Right? Do we understand this point? Mhm. All right. So I'm going to stop sharing this. I'm going to come back to the original. Okay. So this is what we did on the other image. I'm going to draw this roughly over here, and I will also share that image with you. So this is the extended object having approximately the same distance. This is our eye that we want to cover up. And then we start from this point with dotted lines covering the lower part, then dotted lines covering the upper part. So the lower part is successfully visible. Let's move to the upper part. So dotted lines covering the upper part, then dotted lines covering the lower part. Then we simply have to join back them again with this. So lower with the black one, and red is with the upper one. So what's basically happening is that all of these light rays are actually bouncing off from the mirror and then successfully coming to the eyes. Now, one more thing that the trick that I've discussed with you, that how to draw this completely accurately, is this one, that you start from this way or start from this side. This will also help you establish one more thing. Let's come at this point again. I'm going to draw just one light ray to show why is this necessary. What are we trying to do over here? So at this point, we have when the light ray actually bounces off the mirror, what actually it's trying to follow at this point, since it's reflection, if I draw the normal at this point, the angle of incidence and reflection are supposed to be equal. When you draw them directly from the real side, like this way, and bring it to the eyes, it does look nice at that point, but when you extend it back, the angle of normal gets very awkward due to geometrical mistakes. So the better idea would be not to draw this first, but to extend this back and draw this line first and then carry it back to the object. In this case, whatever or however you try to draw the diagram, the angle of incidence and angle of reflection will always be right, no matter even if you draw it quickly. Do we understand this idea? Right? So yeah, yeah. And be also advised that visually speaking, both angles will be different. You see, this normal and this normal will be producing different angles. Right? And to exaggerate or to understand this completely, why is that so? Just notice what's happening over here is that an object generates two light rays like this, and the other light ray is like this. I'm exaggerating it deliberately, considering that this is the size of the eye to explain what's actually happening. Don't try to force this solution because you thought that would be the correct answer onto the diagram. You see, if I draw the normal at this point, this angle of incidence and reflection are different, and this angle of incidence and reflection are different. Do you see that, visually speaking? Exactly. At different places. Exactly. They're hitting at different angles, they're hitting at different places. So even for MCQ questions, what he does is to trick the students. He visually makes sure that these angles are same for both points of incidences. That will be the incorrect option. And sometimes what he does is that he chooses an option or presents an option that are actually parallel to the light, like this. The both lines appear parallel. This is wrong. The light rays have to appear diverging away from each other for the eyes. Do we understand that? Right? So these are all the little tiny bits or limitations presented by the examiner to confuse the student. Okay. So any problems in line tray diagrams? Okay, good. So let's move ahead with the The ray diagram of lenses. Ray diagram of lens. So it has three rules. The rules are not mentioned in the book. It is, you can say, I figured them out as a student when I was giving my O levels. So I've always taught my students the same way because it leaves a lot of hassle out of solving the question and it makes it easier to understand and easier to solve. So I'm going to share the same technique with you, what I used to do. And it will ensure that all of your diagrams are always going to be correct, even if you are not prepared for this chapter. So the first trick or the first rule is that, okay, not this way. First, we have to learn the anatomy of the lens. So before the ray diagrams, we need to understand what a lens and every diagram is. So the line that we draw as our reference is known as the principal axis. And wherever we place the lens like this, we can't draw this again and again. So what we do is we just replace the lens with a straight line like this one. Okay. So the principal axis and a straight line. This is what you will see in the examination. So this vertical line will be the lens and this horizontal line will be the principal axis. The principal axis does not exist in real life. It is just a reference line where we place the object like this, right? Okay. So wherever the light rays actually focus, for example, this is a converging lens, wherever the light rays are going to focus after crossing the lens, let's say this is that point where they focus or converge. This point will be known as the focal point. And this length from the lens center to the focal point will be known as the focal length, right? And this one special point that is over here where lens crosses the principal axis is known as the optical center. These definitions and terms are not a part of your course except the focal point, focal length, and principal axis. Optical center is not a part of your course. But I'm just discussing that because the rules that I'm going to tell you will involve this. Yes, do we understand this point? Any problems with the terminologies? Okay. All right, all right. So there's another term when you go for higher levels after A levels. I'm sure you'll have to go through the entry test to go through the universities. There is another term that is known as center of curvature. It's not a part of your course in O levels anymore, but it's interesting to visualize it this way. You see, how they look at lenses is that they're actually a part of two circles or arcs of two circles. Mathematically speaking, what they're trying to say is that both sides of the lens may have been part of a circle or an imaginary circle. Let me draw that circle for you. So this side of the lens may have been a part of a circle like this one, and the other side of the lens may have been part of this side of or another circle that is imaginary. Of course, it doesn't exist over there, but this is how we visualize lenses mathematically. We represent the focal length, of course, at higher levels, not at O levels. These curvatures and these lines are actually a representation of a circle that is much bigger than that. So we only take certain arcs out of that and try to visualize the lens. Okay. Now, the term center of curvature means that the center of this imaginary circle is known as the center of curvature. So this lens must have been part of a larger circle like this, and this one may have been part of a different circle like this. Do we understand the visualization? Right? So yeah. So the principal axis is basically a point that's or the line, imaginary line that crosses through the center of curvature, optical center, center of curvature, and then forward. And please be advised that the focal point and center of curvature are two different things. They are not the same. Okay? All right. So let's move ahead with the rules that we have for ray diagram. Actually, this would be a better idea. I only have 2 to 3 minutes left for the Zoom class.